Hello and welcome to this film, which is all about acid and base strength. Now hopefully by now you know what is meant by an acid and a base and by a conjugate pair. In this film we're going to look at how the strength of an acid and a base will influence how they're represented in hydrolysis equations, and it will also determine how strong or weak their conjugate pair is. Right, so to begin with we're going to have a look at this list of important acids which hopefully you saw in the introductory film about acids and bases. 3 of them are highlighted in green. They're the 3 strong acids that you're going to need to remember for the IB course. They're not the only 3 strong acids in the world, they're just the 3 that you need to remember. If you remember that those three are strong, then basically every other acid that you come across is going to be weak. The only exception to that rule would be if they told you in a question so and so acid is a strong acid and went on to tell you stuff about it, then that's the only time you'd come across a strong acid that wasn't one of these 3. So make sure you remember that hydrochloric acid, nitric acid and sulfuric acid are the strong acids and all the others are weak. Now what do we mean by strength and weakness? Well, here are 3 diagrams that show what we mean by electrolyte strength. And that is to say, what happens to a substance when we dissolve it in water? We've got 3 cases here. Right? We've got the first diagram here which shows us a substance which when dissolved in water turned into ions. We've got a substance here which when dissolved into water seemed to partly turn into ions and partly not do anything, and another substance which didn't turn into ions at all. Now we call these 3 types of electrolyte strong electrolytes, so that is ones that completely split up into ions when we dissolve them in water. Weak electrolytes, which only partially ionize when we dissolve them in water, and non-electrolytes, which dissolve in water but don't break up into ions at all. So electrolyte strength does not tell us about how soluble something is, it just tells us what happens to it when we dissolve it in water. And what we can say about electrolyte strength is exactly what we can say about acid and base strength. So in other words, a strong acid will ionize completely, a weak acid will ionize partially, and well, non-electrolytes aren't really very interesting when it comes to acids and bases, because if they don't split up into ions at all, then they're not H+ donors and they're not acids. Okay, so bearing in mind the difference between strong and weak acids, let's have a look at how we write their hydrolysis equations differently. Now these equations are no different to the equations that we saw in the film about conjugate pairs, but you might have wondered in that film, why do some of them look a little bit different to others? Now here is one of our 3 strong acids, hydrochloric acid. We've seen before that its conjugate base is the chloride ion and it gives away H+ ions to water. What we might have noticed here is that it's got this one-way arrow in it. Now because it ionizes completely, what this is telling us is that every single molecule that we put into water is going to turn into a chloride ion and give H+ ions to water. Right? So in other words, this is a one-way reaction. All our reactants turn into products. That's what we mean by a strong acid. It ionizes completely. Let's have a look at a weak acid and how the equation looks different. Well, apart from the fact we've got different reactants and products because we're using a different acid and its conjugate base is now different, we've also got this really important difference, which is this 2-way arrow. Now, if you've done the equilibrium topic, then you know that this shows us that the forward reaction happens and so does the backward reaction. So in other words, not only does ethanoic acid give H+ ions to water, but the ethanoate ion can accept H+ ions from H3O+ and turn back into ethanoic acid. Now if you're a weak acid, like ethanoic acid, that means that not all of these reactants have turned into products when we reach equilibrium here. Right? So in other words, if you took a beaker of ethanoic acid and zoomed in on it so that you could see all the different particles in the solution, you'd see lots of ethanoic acid molecules and lots of ethanoate ions. And in actual fact, for most weak acids, the unionized molecule, so in other words the ethanoic acid here, vastly outnumbers the ionized form. That's not true for all weak acids, but it's true for most of them. Let's have a look at sulfuric acid. Now you might have noticed something weird going on here when you first saw the hydrolysis equations for sulfuric acid. We've got both a one-way arrow and a two-way arrow. Now this is because sulfuric acid is a strong acid. If you put it in water, all those sulfuric acid molecules will give away H+ ions and turn into hydrogen sulfate ions. We might also remember that sulfuric acid is diprotic. That's because the hydrogen sulfate ion can give away another H+ ion to water and turn into a sulfate ion. However, hydrogen sulfate ions are weak. They don't completely split into ions. So that's why we've got a two-way arrow here and a one-way arrow in the first hydrolysis equation. Let's look at a weak base, ammonia. And here we can see ammonia accepting H+ ions from water, and once again we've got a two-way arrow, which means that only some of the ammonia molecules in my solution will have accepted H+ ions from water by the time we reach equilibrium, and there will be some ammonium ions in the solution, but there will also be some ammonia molecules. And if we're SL students, then we really don't need to worry about what proportion of ammonia molecules have turned into ammonium ions. If we're doing HL, then we'll do that in a little bit more depth. Now, let's just finish up by again looking back at equilibrium and deciding what the strength of conjugate pairs is going to tell us about where the position of equilibrium is going to be. Okay, now in this equation we've got hydrogen bromide and hydrogen chloride, or hydrobromic acid and hydrochloric acid. Now we should be looking at this and thinking, oh, here's a strong acid, right? We should also be looking at it and thinking this is a weak acid because it's not one of those three that we were told about. Now if that's the case, and HCl is very good at turning into chloride ions, and HBr is not quite so good at turning into bromide ions, then we would expect, if the forward reaction happened and HBr gave H+ to chloride, that HCl would be better at giving that H+ ion back to bromide and turning back into the reactants. In other words, we'd expect this equilibrium to lie over to the left-hand side and for the forward reaction to happen to a lesser degree. Another way of saying this is that if HBr is a weak acid, then its conjugate base must be quite good at accepting H+ ions, and it therefore must be quite strong, which is why this backward reaction is able to happen more than the forward reaction, because bromide is taking away H+ ions from HCl in the backward reaction. On the other hand, if HCl is a strong acid, that must mean that its conjugate base is very bad at accepting H+ ions, or in other words, it's a very, very weak base, which means that it's not going to take H+ ions away from HBr, and the forward reaction isn't going to happen very much. So in other words, if you're a strong acid, your conjugate base is weak. If you're a strong base, your conjugate acid is weak. And if you're a weak base, then your conjugate acid must be quite strong, and so on and so forth. Right, we've reached the end of this film. Hopefully it all makes sense. If you've got any questions or comments, then please feel free to come and see me or to post a comment on YouTube.